All right. Now, today we will start the new chapter, which is called Linear and Time Invariant Systems. Which combines the two most important properties of the systems that we have started, right? Linearity and time invariance. But particularly when they are combined, they form a very valuable set of systems that are very suitable for analysis. We will be able to analyze linear and time invariant systems with some very nice mathematical tools. We will say that it's causal. We will say that it is stable, just by looking at some very specific properties. Previously, if you remember, in the last week, I gave you only by examples saying that it is causal or stable. But now, if they are in this particular class of linear and time invariant systems, then saying the answer to whether it's stable or causal, etc., will be much easier. By saying much easier, I don't mean that we will immediately find the results for those questions or the answers for those questions. Of course not. It will take the whole semester to be able to properly answer the causal and stable questions. But at least we will have the tools. Let's start by briefly reviewing what this linearity and time invariance was. Time invariance was like this. By the way, there's an abbreviation to linear and time invariant systems that is called LTI systems. This abbreviation LTI corresponds to that. In the previous years, once, I guess several years ago, I asked this. What does LTI stand for? That was an exam question, a very simple 1 point or 5 points, a small exam question, and lots of stupid answers were made. Some of the students didn't even know what LTI means. LTI means linear and time invariant. I remember answers like literature and local something, lots of nonsense regarding what it stands for. For our course, it stands for linear and time invariant. So we will say LTI systems now. The time invariance, TI, was corresponding to this. If your system behaves like this for all inputs and output, it has a particular input, let's say x of t, and the output of the system is y of t, then, x of t minus t0, that is shifted version of the input, will have to provide you with the shifted version of the previous output. This is time invariance. This is a very physical property for a natural system. For a physical system, the systems are almost always time invariant. They don't depend on when you are running that system. You may run it today and the output will be delivered today. If you run it tomorrow, it will deliver the output tomorrow. Okay, that's a natural consequence. And the linearity was something like this. If x of t comes into the system and y of t goes out, but I will give numbers to that. x1 of t will produce y1 of t, and x2 of t will produce y2 of t. These must be individually observed. You make experiments, black box experiments. You apply this input, you observe that output. You apply another input, you observe the other output. Then somehow, if your function generator is able to linearly combine the inputs, there must be B, where A and B are just complex in general, or real numbers, variables, just scalars in other words, coming into the system. It will have to produce the same scaled version of the answer to the first input, the response to the first input, plus the same scale with the answer to the second input. So when you combine several individual inputs, the corresponding outputs will also be combined. That is linearity. Now with these two combined, we will be able to come up with a very nice way of representing the input-output relation for a system. And strangely, by knowing only the input-output relation, a particular input-output relation, it will be suitable for us to find any output to any input. How can it be? Let me try to formulate a question. Suppose that, by the way, writing these things or giving examples to the situation of linear and time invariant systems in discrete time is easier. So I will give you an example of a discrete time. Okay, this is the axis of n integers. At 0 and 1 time instances, the outputs are 1 and 1. So this is our input, x of n. X of n goes into our discrete time system. Now, of course, if the input is not continuous time, it must be a discrete time system anyway. And we observe the output y of n. So x of n is this, and y of n is, I don't know, just some shape over n. Let's say 0, 1, and 2. At these time instances, the output is 1 and 2. So at 1 it is 1, at 2 it's 2. If the input is that at the top, then the output is the one at the bottom. By the way, does it look causal to you? At least intuitively it looks causal, because the output starts to exhibit itself after the input is applied. The output comes later. So it's a causal system. And all the others are zeros. Okay? If the input is like this, all the others are zeros, and at 0 and 1 you have 1, 1, and the output is 1, 2 at 1 and 2, n is equal to 1 and 2. This is an input-output relation. Now, if you make this black box experiment, can you solve this question? It's not an example, sorry, it's a question now. Suppose you have an x prime of n, a new signal. Which is, at 0 it is 1, at 1 it is 2, and at 2 it's again 1. All the other values are zeros. Okay. X prime of n is given like this. So the question is, what is y prime of n? Without repeating the experiment, without doing any further black box experiment, can you find the output? The screen is a little bit small. Yeah. Let's look at the situation like this. So we have the top input producing the middle thing as the output. And now I say that it's not the top thing that I input. This time I'm gonna input this, x prime of n. Can you analytically describe what y prime of n is? What's the response of the system to this input? Any suggestions? I'm not asking you the result. I'm asking you how to attack the problem. Yeah. Giving odd numbers. I don't think I quite understand what you're talking about. I don't know. Is that the way to attack the problem? How could you solve this? Now, one thing that I didn't mention, and if I don't mention it that way, you should be telling me that, well, sir, we cannot find the result if you don't give us any information about the system S, at least in terms of the properties. Then I have to tell you that it's also given that this S is an LTI system. So it's a linear and time invariant system. Now you should be able to tell something. Okay, if it is linear and time invariant, there's something that I can do. And the best way to do is to decompose your input, the new input x prime, in terms of a known input. What is the known input for this case? The top one. So you should attack the problem in that way. Can you write x prime of n in terms of x of n at the top? And the answer is yes, because I deliberately constructed this simple example to satisfy that kind of a relation. X prime of n is easily represented in terms of x of n. Yeah, just look at the top figure. Take the same figure and shift it to the right by 1. And then add the two signals. One of them is therefore x of n, the other one is x of n minus 1, one shifted version. Then two 1 samples at 1 will be combined to form a 2, and the others will be 1. So it will be 1, 2, 1, just like this x prime of n. So x prime of n is quite simply x of n plus x of n minus 1. Okay, that's how I constructed this shape. And we know that this is a linear and time invariant system. So what would be the response to x prime of n? It will be called, let's say, y prime of n will be equal to what? It will be the response to this. What is that? Y of n. This shape in the middle at the top. Okay? So that is y of n. That component will produce y of n. Plus, what will this produce? Y of n minus 1. Why? Because it's a time invariant system. And why is the combination of the outputs? Because it's a linear system. So it's a linear and time invariant system, therefore this equation holds. Y of n plus y of n minus 1. What was y of n? Y of n was this. What was y of n minus 1? It is one shifted version. So at 0 and 1 it is zeros. At 1 it's a 1. Sorry, at 2 it's a 1. At 3 it's a 2. And the others are zeros. Okay, so let's combine these two. Let's add them up. What's the summation? That is a summation operator. You just add them up. That is a 1 at 1. Because it's 1 plus 0. Okay, as you see. And then 2 plus 1 is 3. So this is 1, this is 3. And then 0 plus 2, it's a 2. So 0, 1, 2, 3. After 3, all of them are zeros. Nothing contributes. Before 0, it's always 0. It's again. So this is the result. This is y prime of n, the summation of the top two. So, and I found the answer without repeating the experiment. I only have this top experiment, input-output experiment, and from there I now constructed a new input. I now have a new input which is like this, I want to know the answer, the response of the system. And after combining itself and its shifted version, because the input is constructed that way, I get y prime of n like this. Is this clear? So linear and time invariant systems help us to write these equations. If the input is a combination of some known inputs, then you can, by saying known inputs, the outputs, the responses are known, then I can just combine the individual responses by shifting, probably by scaling too. Let's have a different question from the same input output. This time x prime of n is given like this: 1 and 3 and 2. That's 2. The others are zeros. Can you find the output? Again, the trick is to try to represent x prime of n. It's a different x prime of n in terms of the original x of n at the top. What is it? Well, it's equal to x of n plus 2 x of n minus 1. I mean, if you check the numbers, you will see that 1 1 here and 2 2 here. One shifted version of 2 2. There will be a 1. There will be 1 plus 2, which will make a 3, and a 0 plus 2, which will be a 2. Do you agree with this formula, this equation? So the input drawn here is like this. And can you then find the response, the output? The output is y prime of n is equal to y of n from this first part plus 2y of n minus 1 from this part. You just have to draw them, add them up on top of each other, and you will find the result. So the answer is this: y prime of n is equal to y of n plus 2y of n minus 1. So this scale by 2 here also automatically scales the output. The shifts are automatically shifted. The combinations are automatically combined at the output. That's what it is. Now, another question. Again, we have an x prime of n, which is 1, 2, and 1. That's 0, 1, and 2. All the others are zeros. Oh, yes, fine. Can you find the output? Now, I'm expecting the results from you. If you can't find it. Huh? Yeah. Sorry. This is the first example. It's the same as the first example. Excuse me. I'm altering the input. Let's make it 1 1 1. Okay. A different one. Now, what is x prime of n in terms of x of n? Yeah? Any suggestions? What is x prime of n in terms of your known signal x of n? Well, as far as I can see, there's a problem here. I cannot immediately represent or express x prime of n in terms of x of n. It may even be the case that it's not representable in terms of x of n. Then what? Then what shall we do? How can we proceed? The answer to this is we cannot proceed. We cannot proceed because we are unable to represent our signal in terms of our known signal. So that is a problem about our known signal. Our black box experiment has a flaw. It has a problem. And the problem is that this top x of n here is not generic enough. We cannot really express all signals in terms of shifted and scaled combinations of this top x of n. It doesn't span the space of signals, discrete time signals. It doesn't span. You can represent only some limited, a lot of them, infinitely many, but still a limited number of signals will be decomposed into this x of n and its shifted versions. Scale, those scales could even be negative, okay? Keep in mind that. Okay, I'm always giving you examples about positive scales, but it doesn't have to be positive. They can be negative, then the outputs will be negatively scaled too. That's not a problem. But the problem is, as I say, you cannot represent all your signals, not all of them, in terms of this. This is an example. We have a problematic case here, which is not very easily represented in terms of the top one. Probably it will not even be represented in terms of that at all. There's no way, maybe. So isn't it a better idea to make the input-output black box experiment not with these two impulses, but instead with this one? And at 0 it is 1, and at everywhere else it is zeros. This is the input, and it goes into the system, and the output is y of n, which is, let's say, like this. By the way, this output is completely arbitrary, okay? I'm just inventing that. This is 1, this is 2, this is minus 1 at 0, 1, 2, and all the others are zeros at all the other indices, okay? And this is an LTI system, okay? This is a necessary condition. Then this input-output relation magically solves all the problems, because it's impossible to be unable to find your signal, your input signal, in terms of this x of n. This x of n is the most generic input. By the way, it had a specific name. Do you remember this? It was the unit sample or unit impulse, delta n. Okay. So if you apply a unit impulse in the as the input, then its output is measured. Now, no matter what I give you as a question of x of n, x prime of n, let's say minus 0.5, 0, 2, at minus 1, 0, and 1, and all the others are, let's say, zeros. So this is x prime of n. All right. What is the output? How will you find the output? Then this x prime of n, I can immediately say that that is equal to minus 0.5 times x of n plus 1, which is the negative impulse at minus 1, scaled by 0.5, plus 2 x of n minus 1, shifted to the right, and scaled by twice. So what is y prime of n then? The same equation. Minus 0.5 y of n plus 1 plus 2 y of n minus 1. Okay? This will be the response. And all you need to do is you need to scale the sample output y of n, this one, and scale it by 0.5 or 2 or whatever, or minus 0.5. If it is scaled with a negative, all the values will be negated and scaled respectively. And if it is y of n minus 1, it is shifted to the right. If it is y of n plus 1, it is shifted to the left. And you have to just sample by sample combine the results to accumulate and find the output. I guess you can draw it, right? You can draw this y prime of n, I hope. Okay. Whatever I can think of as x prime, it is representable in terms of this particular x, which is the impulse. And the representation is this. I will say it's like this. Any x of n is equal to ... plus x of minus 2 times delta n plus 2 plus x of minus 1 n plus 2, sorry, x of minus 1 delta n plus 1 plus x of 0 delta n plus x1 delta n minus 1 plus x2 delta n minus 2 plus ... As simple as that. Every signal, every discrete time signal can be decomposed into discrete time impulses. But that's clear. There is an impulse here. What is the value of that impulse? For example, this is an impulse at n is equal to minus 2. Okay? That one at the top. What is the magnitude of that? Its magnitude is whatever it is. It's x of minus 2. Depending on the question, I will draw it, I will give it to you. So it is x of minus 2, whatever that scale is. It may be positive or negative, small or large. This, the second one, the next one, is an impulse at minus 1. What is the scale of the signal at minus 1? Its scale is x of minus 1, the value of the signal at that point. This is an impulse at 0, so the value is x of 0, etc. This is an impulse at 1. It's the magnitude of that impulse is the signal's value at that point, which is x of 1. You see, this is a very generic way of representing everything. For example, sorry? This is n minus 2. Instead of 2's, I'm constantly using some erroneous things. I'm not very well today, so I can make a lot of mistakes, typographic things, and please warn me immediately whenever you notice. Don't hesitate about that. So this combination, how can we visualize that combination? For instance, let's think of a signal with some values at minus 3, at minus 2, at minus 1, 0, 1, 2, 3, etc. This is your x of n, you see? And clearly, it is a combination of shifted impulses. And what are the values? For example, what is the value here? the value there, it's parametric. We don't know what it is, but its value is x of minus 3. That is the value. And the value here is x of minus 2. The value here is x of minus 1. The value here is x of 0, x of 1. You see? These are the values, parametric variables. But they are impulses. So this value of x of minus 3 is scaling an impulse at minus 3, that is delta n plus 3 here. So that's what it is. So, and we have another combination, x of minus 2 times delta n plus 2. It is this impulse, this impulse, this impulse, first, second, third. All these impulses will form our signal. So it's impossible for you to fail a representation in terms of impulses. An impulse is the fundamental building block, the Lego brick, okay, of your discrete time signals. You can build everything from those Lego bricks, which is the unit sample or the unit impulse. But for the time being, I didn't write the compact form. Let me write the compact form. I just said dot 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 plus something and then plus dot dot dot. But that has a formula, in fact, a very compact one. It's an infinite summation, but in that infinite summation, some of the scales may be zeros. So this is the most general form of putting things. That is equal to m from minus infinity to infinity, x of m delta n minus m. Is that okay? Yeah. I think I didn't make a mistake there. I was a little bit confused about running indices and things like that. But for example, the top one is just an intermediate summation portion of this infinite sum. If x of m, these scales here, are zeros for very small m's, or if they are zeros for very large m's, then it will be a summation in the middle only, from minus 10 to 20, from 0 to 5, whatever. But this is the most general way of putting things. And it's a formula that you have to nail, right? It's a very, very important one. You have to remember. If you're uncomfortable with the formula, if you cannot really derive it, then it's better that you memorize it. This is something that you need to memorize. This is the formula to represent your signal in terms of impulses. You may say things like this. We have a signal here, and we are using the same signal at the right-hand side to represent it. And I will say you are wrong. The left-hand side is a signal where n is the free time variable. The right-hand side, x of m, is not a signal. It's a value for every m. Summation from m equals minus infinity up to plus infinity for every m. For example, for m is equal to 3. X of m is x of 3. It's a value. It's a scale. It's not a signal. It's a scale. So where's the signal? The left-hand side is a signal. At the right-hand side, I say x of m is not a signal, it's a scale. So what is the signal at the right-hand side? It's delta. It's a signal. Inside it there is n. And then it is shifted by an amount of m. It's just a combination of shifted impulses. Scaled by m and shifted by m. Scaled by x of m and shifted by m. It's a linear combination of all these individual impulses, for example. I sum them up indefinitely from minus infinity to infinity. This is an important formula, and it is known as convolution sum. It is the convolution sum. The terminology, the term convolution will be used all through this semester from here on. Convolution has an interesting Turkish, and I don't even remember that. Evrişim or something like this. Evrilme, bükülme. I don't know. I never thought about that. But it is just bending or flipping sort of thing, and then operating upon. That kind of an awkward meaning. But it's a terminology. Don't worry about the meaning of that. It's just convolution. And this is called the convolution sum. It represents your signal your discrete time signal in terms of scaled and shifted impulses. It's the representation of your signal in terms of shifted and scaled impulses. But now, since the window size at this scale is very small, I will have to repeat something. Do you remember the linearity, and do you remember the time invariance that I have just made? In the linearity, I said that if you combine two inputs, the outputs are combined. So what are we doing? We are combining impulses at the input. So the outputs must also be a combination of the outputs. And knowing the response of your system to a single impulse is enough, because all the other inputs are just shifts of that. So the outputs will also be shifted and scaled, so the outputs will also be scaled simultaneously at the same time. Let me write the convolution sum again. This is the representation. X of m's are scales and m is the shift. When you input this into an LTI system, if the system has this property, then we have an amazing output. Y of n is equal to the same summation. We are combining the inputs, so we have to combine the outputs. How do we combine them? By summing up m from minus infinity to infinity. Let's give a name, a particular name, to the response to a single impulse in the center. Do you remember the question? Yeah, here. The input was delta n. The output is y of n, I said. But y of n is the output to any x of n. So let's give a name to that, a particular name. We have impulse, we have unit step. These are the specific names, for example. This one also has a specific name. It is deliberately indicated by h of n. H is a very commonly used system response terminology letter. H of n is what we are going to use. And since it's the response to an impulse, its expansion, h of n is the abbreviation, and its expansion is impulse response. You have to measure the impulse response of an LTI system in order to analyze it completely. The way to analyze your system is to find the impulse response. You have to measure that. It has to be given to you. Now, suppose that for every delta, for a delta n, the response is therefore h of n, the impulse response. Then what is the response to delta n minus 1? It's a different question. What is the response of the system to delta n minus 1 in terms of h of n? H of n minus 1. To delta n minus 2, the response is h of n minus 2. How about 2 times delta n minus 2? The response is 2 times h n minus 2. How about the response to x of 2 times delta n minus 2? The response is x of 2, h of n minus 2. Then look at this term, x of m delta n minus m. What is the response? X of m is the same scale. It doesn't change. Every delta n minus m will be responded by h of n minus m. This is y of n. You're saying, is this x of m or y of m, right? You're asking that. It is x of m, because x of m is a value. It's just a scale. It's like 3, 4, 5. At a particular value of m, it's a value. So it's a scale, and the output is scaled with the same scale. The input is scaled by xm. The delta is scaled by xm. H is also scaled by xm. So this is x of m, h of n minus m. So this is the response. And it's a very useful formula. I'm very proud of this formula. Okay? Let's nail it. It has a name, of course, just like all the other things that we covered today. It is called the convolution this time. Convolution requires two parameters. If it's not a convolution sum, if it's a convolution sum, it corresponds to the specific case that h is equal to delta. But in general, for any given h and for any given x, this is the convolution of x and h. It's the formula for the convolution of x and h. Now, the rest of the system analysis under the assumption of linear and time invariant systems, and that assumption is a very strong one. Okay, all of our systems will be linear and time invariant. So under this assumption, the way to find to determine the output of the system to any input is through performing this summation. You have to, of course, perform or evaluate that. All right. The question is, can you evaluate it? If I give you an h and if I give you an x. Well, there are several methodologies to do that. But at least you should be able to do this. Just split your x into impulses. In order to solve it graphically, okay, using graphics, it must be a short x and it must be a short h. Otherwise, if they are very long sequences, it will be a headache to perform this convolution one by one. It will take hours and you won't be able to solve the question on time if it's an exam question, for example. So in the exams, you will be perhaps given some very short x and h. The first thing that you need to do is you have to split your x into impulses, and then for each impulse you need to evaluate the corresponding h. If the impulse is here, the h will be here and scaled by the amount of impulse at the input. If the impulse is shifted one, then the h will also be shifted and scaled with the same input. That's what you need to do. I will do a simple example, and after that we will give a 15 minutes break. Suppose that your impulse response is given. So for a system, in order to represent a system, from now on I am going to give you the impulse response, and that completely describes your LTI system. So h of n is 1, 2, this, which is the response to an impulse, you know that. And then I have to give you, of course, x of n, which is minus 1, 0, 1. At minus 1, 0, and 1. And all the others are zeros. So this is the input. What is the impulse response? How will you find it? As you see, you have one impulse here, which is delta n plus 1 shifted to the left and scaled by minus 1. what is the response to that? The response to this first one, it may be a good idea to use color, but the color is not very visible from the projector, but it will be visible in the videos. So the red one will produce a response like this. The one shifted version of the top to the left, so it must start from -1, not from 0, but it must be also scaled by -1. So it will be -1 and -2 at -1 and 0. So this is the response, okay? This one and this one, these two. Now I will use a different color, which probably you will not be able to see. The blue one, this one. What's the response? The response to that will be this blue figure, which is an impulse shifted to the right. So the impulse response at the top must be shifted to the right and scaled by 1. So it doesn't need to be scaled, just keep it as it is, multiplication by 1. And the response will be this and this, 1 and 2 at 1 and 2. The others are 0. And then finally, all I need to do is to add this top red and bottom blue. Figures. So this is a summation, and the summation is -1 plus 0 is -1 here. -2 plus 0 is a -2 here. 0 plus 1 is a 1 here. And 2 plus 0 is a 2 here. So it is -1, -2, 1, 2. At -1, 0, 1, 2, and all the others are zeros. So this is y of n on an axis of n. If I give you more samples of h or more samples of x, then the number of summing terms will be more, of course. Okay, you will have to sum up as many as the input impulse number. Here the input has only 2 impulses, this one. But if it has more than 2, then you just have to add as many responses as possible. Shifted and scaled responses. You have to sum them up. This is how you should be able to solve the graphical response problem. Will you be able to do that? You should be. For at least small signals, you should be able to do that. If you're not able to do that, well, you have to work on it. Just study this one a little bit. Now we can give some 15 minutes break. After the break, we will continue. Sorry. All right. Okay.